and we're going to try to get our exponential stuff done before lunch, and we'll come back and do some logistics stuff. Hopefully. So, first thing, you're still working on your quiz, go ahead and get it wrapped up. First thing, I want to just do a quick review of what a regular a regular exponential function looks like. So, you should know this from your BFS, right? You should have an idea of the general shape. Well, I'm just going to plot a few points here. This is a little exponential. Remember we talked about if the variable is the exponent, it's going to be exponential. The base can be anything. In this case, it's 3. But you need that x to be able to be the exponent. So that's what we got. Basic, simple, probably the simplest little exponential. What happens if x is 0? 1. Now, that point isn't going to change. If I made this 3 to the x, wouldn't that still be there? And in fact, when you did your BFFs, it was e to the x, but that point was still there, right? All right, what happens if x is 1? 2. What if it's 2? 4. And this is when we see this kind of action, right? Shooting up really, really fast. Okay, well, what happens in this direction? What happens if x is negative 1? Then it's 1/2. And if it's negative 2? 1/4. And that's where we see this happening. Will this value ever come out negative? No, but it's going this way, it's going to continue to get smaller and smaller and smaller. So the end behavior for an exponential function, remember, end behavior, this is our notation, is what? What is the end behavior for a regular exponential function? Well, as we go to the right, what is happening to the curve? It's going up. What if we're going to the left? It's going to 0 from the top. And that's going to be the case anytime you have an exponential growth function.
For 0, if we're coming from the top, would it be positive?
It should be a plus, thank you. 0 from the top. This is a growth function. Obviously, the thing is getting bigger and bigger and bigger, right? Now, it's possible for exponential functions to be decay functions. So let's look at this first one right here. And I'd like you to think about this for a second. What is 3 to the negative second?
1/9.
So this is really just another way of saying 1/9 to the x, right? Now let's talk about that one. Certainly, if x is 0, I still get 1. That isn't going to change. But what happens if x is 1? I get 1/9. And if x is 2, I get 1/81st. Or what if x is negative 1?
9.
I get 9. So do you see what I mean? That it's possible for an exponential to be a decay? Well, why is that one growth? Why is this one growth and this one decay? What can you notice about their bases?
Less than 1.
If the base is more than 1, it's going to grow, isn't it? As you raise it to higher powers, it's going to get bigger and bigger. But if the base is less than 1, then it's going to decay. It's going to decrease. Okay, so I'm doing some problems here from the notes. It says, state whether it's an exponential growth or decay and give the end behavior. So I'm going to do all the growth and decay first, and then we'll look at the end behavior. This one's decay. What about this one?
Decay.
Decay. Because the base is less than 1. Remember, E is about 2.718 something, so this is like 1/2. This is small. All right, what about this one? Growth or decay?
Decay.
Decay. And then we've got our tricky one.
Growth.
Yeah, because I'm going to make that 3/4 for a minute. So this is 3/4 to the negative x. What does that negative x do?
Flip it.
So now it's really 4/3 to the
X.
x. So this one is actually a growth. Even though in the beginning you may have looked at this and said, oh, it's decay. No, because it has not only a little number, but a negative exponent, so they kind of cancel each other out. All right, let's talk about end behavior. I don't want to take our time to do all the end behaviors, but let's do this one. We already did. If it's a growth problem, it's going to look like that. Would you agree? And if it's a growth problem and it looks like that, then this is going to be its end behavior. Right? Now, what if it's a decay problem? What if it's like this one, or this one, or this one? If it's a decay problem,
It's the other way around.
then as we go to the right, we get closer to 0. But as we go to the left, we shoot up into space. Would everybody agree with that? All right, so you need to be able to determine whether your equation is growth or decay. That's not hard to do. I think it's easier if you kind of simplify it a little bit, clean it up, and I think it's real easy to tell if it's growth or decay. All right, now you got to sketch a couple by hand, and they're versions of this one right here. So we need to remember what happens when we mess around with our equation. So that's 2 to the x. What happens, do you think, if we subtract 1 from the x? Now think about everything you learned before, including last year. What happens? It doesn't go down. This would go down, right? Oh, I mean, yes, that would go down. What happens when we add or subtract directly to the x? Then we go left or right. And since it's x minus 1, it's going to go which way?
To the right.
To the right. So what that means is every point on that thing right there is going to go 1 unit to the right. Well, the only point that I actually plotted, I'll go ahead and plot another one here, oops. Because we did plot a few of these. I just didn't label them. So if I take the point 0, 1 and move it 1 unit to the right, it'll become 1, 1. And if I take the point 1, 2, it's going to become 2, 2. And let's do one more. This one was negative 1, 1/2, so it's going to become 0, 1/2. How does that look? Does that look okay to everybody? Doesn't have to be perfect. Plot a couple of points, and it's moved to left or to the right. Has that changed its asymptotes at all? Nope, it's still coming down over here. So has it changed its end behavior at all? No, because that's still a growth function. No matter how we've shifted it, it's still a growth. All right, would you try B? See if you can put B together on your paper. Now, there are a couple ways you can think about this. How did you think about it? What entered your head when you saw this? So you thought about it, I think, Peter, as this is 1/2 to the x. So So he said, okay, that's easy, it's just gonna look like this, that's 0, 1 still, it's gonna look like that. Okay. Anybody think about it any differently than that? That is absolutely fine, that is, there's nothing wrong with that. What did you think about, Sammy?
Like you could reflect 2 to the x over the y.
Exactly. When you change the sign on X, remember that's a reflection. And when you change it on X, it's a reflection across the y-axis, right? So if we took this picture and reflected it across the y-axis, don't we get exactly what Peter had? So you can think about it either way, it doesn't matter.
How come like on what we did on the quiz, we would have had it as 1 over 2x, cause that's the difference.
Okay, so you can make this 1 over 2 to the x like that, or 1 over 2x like that?
Oh, there's a question.
Well, is it,
Do you not distribute the x?
you do, but what's going to a power?
X to power x1.
Right? So you are exactly right.
So you do distribute.
The x has to go, the exponent needs to go with both parts of the fraction, but when it's a 1, we don't worry about it. Okay, last one, here we go. What do you think's gonna happen on this one? What do you think's gonna change?
It's just gonna stretch.
Our base.
It's gonna be a stretch. So what that means is, go back to our original curve. I only labeled a few of the points, but what it's gonna do is multiply the y values by 3. So instead of being 0, 1, that point's going to be 0, 3. Does that make sense to you? If you put in 0, aren't you gonna get 3? And then if I put in 1, I'm not gonna get 2, I'm gonna get 6. And -1 isn't gonna give me a half, it's gonna give me 3/2. Who remembers what we said about that number right there the other day? Anybody remember what we said about that? That's the initial value. It's called the initial value. And what that means is, it's the value of the function at the beginning. So if x is 0, that's the value of the function. And I think I told you that the initial value is always the y-intercept. And certainly that played out here. We actually plotted the points, and that's what happens. The initial value is the y-intercept. Okay, so in a minute, we're gonna be doing, or not in a minute, but at some point, we're gonna be doing some word problems. And keep that in mind, that is your starting value. That's your beginning population, your beginning cases of the flu, or whatever it is you're measuring. That's the beginning amount right there. All right, turn the page, look at 6. I don't know if you have ever seen this before or not. You have certainly worked with the number e. All your natural logarithms last year, the PERT formula you used last year, all that uses e. Did you realize that e actually has a definition? And there it is, it's a limit. E is a limit, and that's the definition. I am not gonna ask you to memorize that, but somebody in your future is going to, so get comfortable with it. E is that right there. Interestingly enough, every problem, like this one right here, if I wanted to do it in terms of e, I could rewrite the number 2 as e to a power, because we have these things called logarithms that allow us to change from base to base. We probably aren't gonna wanna do that, but we could if we wanted to. All right, quickly, before lunch, we're gonna sketch 6A, B, and C. Don't worry about the E. The general shape is gonna be the same. These points will be different, don't worry about them. Won't that point be the same? Alright, so with that in mind, this is the shape you want. Don't worry about plotting a bunch of points, just give me a quick sketch for 6A, B, and C. Don't worry about the fact it's an E now, that doesn't change the way the picture looks. So do a quick sketch and then we will go to lunch.
This goes too high. It's too high.
Did you just get a standard old decay for the first one? Just that right there? What happened with that one? That one's kind of an easy one too, right? So this is, I'm gonna go ahead and in a dashed line. That's my basic function, right? What am I doing to that now? What does this do? Picks everything up 2. So she's right, I'll label the 0.03, and then, now it's not changing the asymptote, it's just gonna take it longer to get out there. But it's lifting the whole thing up to every point up 2. What about this one? This is a mess. What? Let's just make a list of what's changing. What's changing in this picture? It's gonna go down 1, for sure. What else is it gonna do?
Reflect.
Reflect how?
On the X.
Yep, reflect across the x-axis. And it's gonna have a vertical stretch. So in other words, your y values are gonna be doubled.
Does it reflect first or does it go down 1 first?
Down 1 will be last. That will be the last thing that we do. So, Liam, a good way to think about this is PEMDAS. If you were PEMDASing this, you would be doing your exponents, multiplication, all of that before that, right? So just follow PEMDAS. Yeah, I gotta get your lunch, people. It's already short today. So we'll finish this as soon as you get back. And I need you back at 45. Need you back at 45. Don't shoot the messenger. That's just how they've set it up. So need you back at 45.